Welcome to this walkthrough of LeetCode problem number 1293, shortest path in a grid with obstacles elimination. In this problem, we'll explore how to navigate a grid while optimizing for the shortest path, even when faced with obstacles. Stay tuned as we break down the core concepts and approaches to tackle this challenge effectively. In this problem, you're given a grid represented as a 2D matrix, where each cell is either empty, denoted by a 0, or contains an obstacle, denoted by a 1. Your goal is to find the shortest path from the top left corner of the grid, at position 0, 0, to the bottom right corner, located at M1, N1. You can move one step at a time, either up, down, left, or right, but here's the challenge: along the way, you can eliminate obstacles, but only up to a maximum of k obstacles. If it's not possible to reach the bottom right corner, the function should return -1. The input consists of the grid itself and the integer k, and the output is the minimum number of steps needed to complete the path, or -1 if such a path can't be found. Let's look at an example to understand this better. Suppose the input grid is a 5 by 3 matrix, where most cells are empty, but there are obstacles in certain positions. The value of k is 1, meaning you can remove at most one obstacle. Starting at the top left corner, you can follow a path that avoids most obstacles, but at position 3, 2, you'll need to eliminate one obstacle to proceed. From there, you continue to the bottom right corner at position 4, 2. In total, this path takes 6 steps, and since it's the shortest valid path, the output for this example is 6. In another example, the grid is a 3 by 3 matrix with many obstacles, and again, k equals 1. Here, despite being allowed to eliminate one obstacle, there's no way to reach the bottom right corner within the given constraints. No matter which path you try, you'll encounter more obstacles than you can remove. As a result, the output for this case is -1, indicating that it's impossible to complete the path. Now consider a simpler case with a single-cell grid. The grid consists of just one cell with a value of 0, and k is 0, meaning no obstacles can be removed. Since the start and end positions are the same, no movement is required. The shortest path length is 0, and that's the output. This example highlights how the problem can handle edge cases where the grid is minimal, and no steps are necessary. Finally, let's discuss some additional constraints and edge cases. The grid's top left and bottom right corners will always be empty, ensuring that a valid start and end point exist. For edge cases, if the grid contains only obstacles and k is insufficient to clear a path, you should return -1. On the other hand, if k is large enough to remove all obstacles, the problem simplifies to finding the shortest path without considering obstacles. The time complexity of this problem is O(m*n*k), because each state, defined by a combination of position and remaining eliminations, needs to be tracked. Similarly, the space complexity is also O(m*n*k), to account for the visited states. These constraints ensure that the solution is computationally feasible even for the largest allowed grid sizes. To solve the problem of finding the shortest path in a grid with obstacle elimination, several approaches can be considered. The first is the brute force method, where we explore all possible paths from the starting point to the destination while keeping track of the number of obstacles removed. This is implemented using a recursive depth-first search, or DFS, which attempts to traverse in all 4 possible directions, up, down, left, and right at every step. Along the way, it tracks how many obstacles have been eliminated and returns the shortest valid path. However, the major drawback here is the exponential time complexity, which grows as O for (m*n) for a grid of dimensions m by n. This makes it impractical for larger grids. A more scalable alternative is the breadth-first search, or BFS, approach, combined with state tracking. Instead of exploring all paths, BFS works layer by layer, examining the shortest paths first. By tracking the number of obstacles eliminated as part of the search state, this method ensures we explore efficiently. The state is represented as a tuple containing the current position, the remaining eliminations allowed, and the number of steps taken so far. This eliminates redundant exploration and makes the problem more tractable. Using BFS with state tracking, the algorithm continues exploring neighbors of each cell. If the destination is reached, the number of steps is returned, ensuring the shortest path is identified. Otherwise, the exploration proceeds to neighboring cells, keeping track of whether an obstacle was encountered and reducing the allowed eliminations accordingly. The time complexity of this BFS-based solution is O(m*n*k), where k represents the maximum number of obstacles that can be eliminated. Similarly, the space complexity is O(m*n*k) due to the visited set, which keeps track of explored states to prevent revisiting and unnecessary computation. The main advantage of this approach is its ability to guarantee the shortest path while avoiding redundant exploration, thanks to state tracking. However, it does require higher memory usage because of the need to store the visited states. Another possible approach is the A** search algorithm, which builds on BFS but introduces a heuristic function to prioritize paths that are more likely to lead to the destination quickly. A heuristic like the Manhattan distance helps guide the search efficiently. While A** can reduce exploration time in many cases, its performance depends heavily on the quality of the heuristic, and its implementation is more complex compared to BFS. Both BFS and A** share similar worst-case time complexity, but A** may perform better in practice due to smarter prioritization. Given the options, we choose the BFS with state tracking approach as our solution for this problem. There are several reasons for this choice. First, BFS guarantees that the shortest path is found, which makes it a highly reliable method. Second, while A** can be faster in specific scenarios, BFS is much simpler to implement and avoids the complexities of designing and fine-tuning a heuristic. Finally, BFS is scalable for this problem because it tracks the complete state, which includes the position, the remaining obstacle eliminations, and the number of steps. This ensures that paths with different elimination histories are treated as distinct, and redundant computations are avoided. One of the key insights here is recognizing that the state must include the remaining obstacle eliminations. Without this, it would be impossible to distinguish between paths that have different elimination histories but reach the same cell. Using BFS also ensures that once the destination is reached, we have the shortest path, as it explores paths in order of increasing length. This makes it both an optimal and efficient choice for solving the problem. There are several important trade-offs to consider when comparing BFS with other techniques like DFS or A*. BFS is particularly well suited for this problem because it explores paths in increasing order of length, ensuring the shortest path is found first. In contrast, DFS, while simpler, is inefficient for this use case as it may explore longer paths unnecessarily before finding the shortest one. When comparing BFS to A**, the latter can sometimes be faster due to its heuristic-driven prioritization. However, A** requires careful design of the heuristic, and a poorly chosen heuristic can negatively impact performance. BFS, on the other hand, avoids this complexity and provides a straightforward, reliable solution. One trade-off for BFS is its higher memory usage compared to DFS, as it requires a queue to manage the exploration and a visited set to track states. Nonetheless, this additional memory usage is a reasonable trade-off, as it significantly improves performance by avoiding redundant exploration. Finally, the complexity analysis confirms the scalability of this approach. The time complexity is O(m*n*k), where m and n are the dimensions of the grid and k is the maximum number of obstacles that can be eliminated. The space complexity is also O(m*n*k), due to the storage required for the visited set. Overall, BFS with state tracking offers a balanced solution that effectively handles both the constraints and the requirements of the problem. In this problem, we're tasked with finding the shortest path in a grid from the top left to the bottom right corner. The twist is that the grid contains obstacles, represented as ones, and open cells, represented as zeros. Additionally, we are allowed to eliminate up to k obstacles along our path. The challenge is to minimize the number of steps required to reach the destination while adhering to this obstacle elimination limit. If it's impossible to reach the destination, we return -1. To solve this problem efficiently, we employ a breadth-first search, or BFS, approach with state tracking. Here, each state is represented as a combination of 4 elements: the current position, x, y, the number of remaining obstacles we can eliminate, remaining_k, and the number of steps taken so far, steps. This state representation allows us to systematically explore the grid and keep track of both our position and our obstacle elimination capacity as we progress toward the goal. To implement the BFS algorithm, we rely on 2 critical data structures. First, a queue is used to manage the states to be processed during the traversal. Each element in the queue represents a state, x, y, remaining underscore k, steps. Second, we use a visited set to keep track of already processed states, preventing redundant work. Each visited state is stored as x, y, remaining underscore k. The algorithm begins by initializing the queue with the starting state 0, 0, k, 0, and marking it as visited. The BFS execution proceeds as follows. While the queue is not empty, we dequeue the current state and check if we've reached the bottom right corner. If so, we return the number of steps as the shortest path. Otherwise, we explore all four possible directions up, down, left, and right. For each direction, we calculate the new position and check if it's within grid boundaries. If the new position contains an obstacle, we verify if we still have remaining eliminations available. If we can eliminate the obstacle, we enqueue the new state with remaining underscore k1 and update the steps taken. This ensures that we explore all feasible paths involving obstacle removal. If the new position is an open cell, meaning there's no obstacle, we simply enqueue the new state with the same remaining underscore k value and increment the step count. We also mark this state as visited to avoid reprocessing. Once all possible moves have been explored and the queue is exhausted, if we haven't reached the destination, we return -1 to indicate that the destination is unreachable. There are some key insights behind this approach. First, BFS is well suited for finding the shortest path in an unweighted grid because it explores all paths level by level, guaranteeing that the first time we reach the destination, it's via the shortest path. Second, we reduce the state space by tracking the number of obstacles eliminated at each cell, rather than revisiting every cell with every possible step count. This optimization reduces computational overhead and avoids redundant calculations. Lastly, we prune infeasible paths early by discarding any state where remaining underscore k becomes negative, ensuring efficiency even in grids with high obstacle density. The BFS relies heavily on the queue and visited set data structures. The queue facilitates level-by-level traversal, and the visited set prevents duplicate processing of states. For complexity analysis, the time complexity is determined by the total number of possible states. In the worst case, there are m*n*, k plus 1 states, where m and n are the grid dimensions and k is the obstacle elimination limit. For each state, we process up to 4 directions, resulting in a time complexity of O(m*n*k). The space complexity is also O(m*n*k), due to the storage requirements of both the queue and the visited set. This complexity makes the algorithm efficient for reasonable grid sizes and obstacle elimination values, as it systematically explores the search space without unnecessary redundancy. When applying this algorithm, it's important to consider edge cases. For example, if there are no obstacles in the grid, the algorithm behaves like a standard BFS and returns the Manhattan distance between the start and end points. If the destination is surrounded by obstacles and k is insufficient to clear a path, the algorithm will correctly return -1. Additionally, the algorithm can handle cases where the start or end cell is an obstacle, as long as k is greater than 0. Finally, for large grids with high values of k, the visited set ensures that redundant paths are pruned efficiently, maintaining the algorithm's feasibility even in complex scenarios. By accounting for these edge cases and leveraging the strengths of BFS, we can reliably solve the problem across a wide range of inputs. Here, we start by importing the DEEC from the Collections module, as it will help us implement the breadth-first search. In the solution class, the method shortest path takes in the grid and the maximum number of obstacles we can eliminate, represented by k. First, we determine the grid's dimensions, and if it's just a single cell, we return 0 because no movement is needed. Next, we define the 4 possible movement directions: right, left, down, and up. These directions are represented as tuples of row and column changes. We then initialize a queue with the starting position 0, 0, the remaining obstacle eliminations k, and the step count set to 0. The visited set is used to track the state of each cell, including the number of eliminations remaining, to avoid revisiting states unnecessarily. Now, while the queue is not empty, we dequeue the first item and explore all possible moves from the current position. For each move, we calculate the new position, NX, New York, and check if it's within grid bounds. If the new position is valid, we calculate the remaining obstacle eliminations after accounting for any obstacle at the new position. If the new position is valid and the remaining eliminations are non-negative, we check if we've reached the target cell, which is the bottom right corner of the grid. If so, we return the current step count +1, as this represents the shortest path to the target. Otherwise, we mark the new state as visited by adding it to the visited set and append it to the queue with the updated position, remaining eliminations, and step count increment by 1. This ensures that we continue exploring all possible paths from the new state. If the queue is exhausted and no path to the target cell is found, we return -1 to indicate that it's impossible to reach the bottom right corner given the constraints. Here, we begin with the Java implementation of the solution. First, we import necessary packages and define the solution class with the method shortestPath. The grid and k are taken as input, where k represents the maximum number of obstacles we can eliminate. We start by determining the dimensions of the grid using rows and COLS. Next, there's a check for an edge case. If the grid is a single cell, the shortest path is 0 since no movement is required. We then define the possible directions for movement, represented as an array of coordinate changes for right, left, down, and up. To implement breadth-first search, we initialize a queue where each element tracks the current position, remaining obstacle eliminations, and steps taken so far. Additionally, we use a hash set to keep track of visited states, ensuring that we avoid redundant computations. With the initial state added to the queue and visited set, we start processing the queue in a while loop, where each iteration represents exploring a possible path. Now, within the while loop, we process the current state by exploring all 4 possible moves using the directions array. For each move, we calculate the new position by adding the direction offsets to the current coordinates. Before proceeding, we check if the new position lies within the grid boundaries. If it does, the remaining obstacle eliminations are updated by subtracting the value in the grid at the new position. If the remaining eliminations, next k, are still non-negative, meaning we can continue, we check if this new position is the target cell. If it is, the method immediately returns steps +1, as we've reached the destination. If the target cell hasn't been reached, we construct a unique state string for the new position and remaining obstacle eliminations. If this state hasn't been visited yet, it's added to the visited set and queued for further exploration, incrementing the step count. This process ensures we explore all valid paths while avoiding revisiting states, optimizing the search process. Finally, if the while loop completes without returning a result, it means no valid path exists that satisfies the constraints. In such cases, we return -1 to indicate that the destination is unreachable given the obstacle elimination limit. This marks the end of the Java implementation for the shortest path problem with obstacle elimination. The approach ensures an efficient exploration of the grid using breadth-first search while carefully managing the remaining eliminations in visited states to avoid unnecessary computations. To begin solving the problem, let's consider a basic example where the grid has no obstacles. The grid is a simple 3x3 matrix filled with zeros, and we are allowed to eliminate up to 1 obstacle, though in this case, there are none. We start by initializing key variables, the number of rows and columns in the grid, the possible movement directions right, left, down, and up, and a queue to facilitate our breadth-first search, BFS. Initially, the queue contains the starting position, 0, 0, with k equals 1, meaning we still have 1 obstacle elimination available, and the step count is 0. We also track visited states to avoid redundant computations, marking the starting state, 0, 0, 1, as visited. In the first iteration, we dequeue the starting position and evaluate all possible moves from there. From the position 0, 0, we first move right to 0, 1, which adds a new state 0, 1, 1, 1 to the queue and visited set, as no obstacles are encountered and the step count increases to 1. Next, moving down to 1, 0 leads to another valid state, 1, 0, 1, 1, which is also added to the queue and visited set. At the end of this iteration, the queue now contains 2 states, 0, 1, 1, 1, and 1, 0, 1, 1. Moving forward, we process 0, 1, 1, 1 next. From here, moving right to 0, 2 results in the state 0, 2, 1, 2, and moving down to 1, 1 gives 1, 1, 1, 2. Both are valid moves, so these states are added to the queue and visited set. The process continues iteratively, exploring all valid moves from each dequeued position, until we eventually reach the target cell at 2, 2. The shortest path length is determined to be 4 steps, which is the output for this example. Now, we analyze a more complex grid that includes obstacles. Here, the grid contains 2 obstacles, represented by 1s, and we are allowed to eliminate up to 1 obstacle. Starting with the initialization, the queue contains the state 0, 0, 1, 0, where we begin at the top left corner with 1 obstacle elimination available and 0 steps taken. The visited set initially marks this state as visited. In the first iteration, from 0, 0, moving right to 0, 1, encounters an obstacle. However, since we still have 1 obstacle elimination available, we transition to the state 0, 1, 0, 1, where k is reduced to 0, and this state is added to the queue and visited. Moving down to 1, 0 does not encounter any obstacles, so the new state 1, 0, 1, 1 is added to the queue and visited. At this point, the queue contains 2 states 0, 1, 0, 1 and 1, 0, 1, 1. Continuing the BFS process, we dequeue 0, 1, 0, 1 next. From this position, moving right to 0, 2 leads to the state 0, 2, 0, 2, which is added to the queue and visited. However, attempting to move down from 0, 1 is blocked because the cell contains an obstacle and k is already 0, meaning no more eliminations are available. The queue is now updated with the states 1, 0, 1, 1 and 0, 2, 0, 2. This process continues, exploring all valid moves and updating the queue and visited set as needed. Eventually, the BFS finds a path to the target cell, 2, 2, with a total path length of 4 steps. Note that the obstacle elimination was used strategically to ensure the shortest path could still be found. The output for this grid is 4. Finally, let's examine a scenario where it is impossible to reach the target. In this grid, almost all cells are obstacles except for the starting and ending positions. Additionally, k is set to 0, meaning no obstacles can be eliminated. During the initialization, the queue starts with the state 0, 0, 0, 0, where we begin at the top left corner with no eliminations available and 0 steps. However, since every possible move from the starting position is blocked by obstacles, no valid states can be added to the queue. As a result, the BFS terminates without finding a path to the target cell, 2, 2. In this case, the output is -1, indicating that it is impossible to traverse the grid under the given constraints. The time complexity of our solution is driven by the breadth-first search traversal of the grid. To understand this, consider the grid size as mxn, where m represents the number of rows and n represents the number of columns. Additionally, let k represent the maximum number of obstacles we are allowed to eliminate. During the BFS, each state is defined by 3 attributes: the current row, the current column, and the remaining obstacle eliminations, remaining_k. The total number of unique states is therefore determined by the number of cells in the grid, which is m*n, multiplied by the range of possible remaining_k values, which is k plus 1. This gives us m*n*k unique states. For each state, BFS explores up to 4 potential neighbors, 1 in each direction, right, left, down, and up. This results in an overall BFS traversal cost of O for *m*n*k, which simplifies to m*n*k when we drop the constant factor. The BFS process terminates as soon as the shortest path to the target cell, M1, N1, is found. While this termination may occur earlier in some cases, the worst-case scenario involves all possible states being visited. As a result, the worst-case time complexity remains m*n*k. Turning now to space complexity, the primary contributors are the BFS queue and the visited set. The BFS queue stores states in the form of row, call, remaining_k, steps, with its size proportional to the total number of unique states, which is m*n*k. Similarly, the visited set keeps track of all previously processed states to avoid redundant exploration. Its maximum size is also m*n*k. Together, these dominate the space usage of the algorithm. In addition to the queue and visited set, there is some auxiliary space required for variables like the directions array and other temporary variables within the BFS loop. However, this space is negligible compared to the main contributors. Thus, the overall space complexity is O, m*n*k. To analyze the computational efficiency further, we can consider three scenarios: best, average, and worst cases. In the best case, the shortest path to the target is found with minimal exploration, leading to a time complexity less than O, m*n*k, and a proportionally smaller space complexity. In the average case, a significant portion of the states is explored before the shortest path is discovered, with time and space complexities approaching O, m*n*k. Finally, in the worst case, all states are visited, resulting in a time complexity of O, m*n*k, and space complexity of the same order. To appreciate the efficiency of the BFS approach, let's compare it to a brute force method. A naive solution would involve examining all possible paths from the start to the target cell, considering every combination of obstacle eliminations. This is computationally prohibitive because the number of paths grows exponentially with the grid size. Specifically, the time complexity would be exponential, roughly O, for m*n, and the space complexity would also be exponential due to the recursive stack space. In contrast, the BFS algorithm avoids redundant exploration by tracking visited states, achieving a significantly more manageable polynomial time complexity of O, m*n*k. A mathematical proof of this complexity arises from the fact that BFS ensures each state, call, remaining_k, is processed only once, and each state requires constant time to explore its four neighbors. Since the total number of states is bounded by m*n*k, the BFS approach is not only optimal but also scalable within the problem's constraints. When working on this problem, there are some common mistakes to watch out for. One major issue is failing to track the remaining obstacle eliminations. If you treat this as a simple shortest path problem without considering the number of eliminations left, you might end up with incorrect results or even infinite loops. This is because the ability to eliminate obstacles directly impacts the paths you can take. Another common error is using a suboptimal state representation in your BFS. If your BFS state only includes the current cell and ignores the remaining eliminations, you might revisit the same cell multiple times with less optimal elimination counts. This leads to redundant work and potentially incorrect results. Finally, don't forget to check grid boundaries. It's easy to accidentally overlook this, but if you try to access a cell outside the grid, you'll run into index out-of-bound errors, which can crash your program. These mistakes highlight the importance of careful implementation and attention to detail. Now, let's discuss a few more common pitfalls. One mistake is processing all states in BFS without proper pruning. If you revisit states that have already been visited with the same or more remaining obstacle eliminations, you're doing unnecessary work. This can lead to excessive computations and even time limit exceeded errors on larger grids. Another misunderstanding involves edge cases. Some people assume the destination is always reachable, but this isn't guaranteed. For example, if the destination cell is surrounded by obstacles and you don't have enough eliminations left to clear a path, it's impossible to reach the goal. In such cases, your function should return -1. By being mindful of these issues, you can avoid common traps and ensure your solution is robust. To perform well in interviews, there are a few key points to focus on. First, your BFS state should include both the current grid cell and the remaining obstacle eliminations. This ensures that different paths with different elimination counts are treated as distinct states, which is critical for correctness. Second, be ready to discuss the trade-off between eliminating obstacles and taking longer paths. The BFS algorithm guarantees the shortest path, but it's important to explain how you balance these factors during your search. Third, always consider edge cases. For example, what happens if there are no obstacles in the grid? Or if the grid is entirely filled with obstacles? What if the destination is unreachable? These scenarios often come up in interviews. Lastly, don't forget to articulate the time complexity of your solution. In this case, it's O, m*n*k, where m and n are the grid dimensions, and k is the maximum number of obstacles you can eliminate. You might also want to mention related problems, such as the shortest path in a binary matrix or finding the shortest distance to a zero in a binary grid. These problems share similar concepts and can help you draw connections during your explanation. Finally, let's explore some alternative approaches and their trade-offs. One option is to use DFS with pruning. While DFS can be simpler to implement, it doesn't guarantee the shortest path and may exceed time limits due to deeper recursive calls. Another approach is bidirectional BFS, where you start searching from both the source and the destination. This can reduce the search space and potentially speed up the solution, but it requires careful handling of obstacle eliminations and merging the two searches. A third option is a asterisk search, which uses a heuristic like the Manhattan distance to guide the search towards the goal. This can reduce the number of explored nodes, but designing a heuristic that accounts for obstacles can be tricky. Each of these approaches has its pros and cons, so choosing the right one depends on the specific constraints and requirements of the problem. Great job! We've broken down the problem, explored the BFS approach, and highlighted key insights. Remember, understanding grid-based problems and using state tracking are critical skills. Thanks for watching, and don't forget to like and subscribe for more content. Happy coding! That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!